Okay then. Okay, so it's now 12 o'clock. This is Automated Software Engineering 2020. This is the session Testing 2. We have 3 talks that will be 17 minutes each with 3 minutes questions. Our first talk is, I'm Tim Menzies from NC State. Thank you to the ASE organizers for putting on such a great show in this time, such a stressful time. Our first speaker is Mohammed Usman from University of Texas, TestMC testing model counters using differential and metamorphic testing.
Okay, so is my screen visible?
Yes, it is.
Okay, cool. Yeah, I'll just move it here. Okay. Yeah. Okay, cool. So TestMC, testing model counters using differential and metamorphic testing. TestMC is basically a framework for testing industrial strength model counters, and it uses concepts like differential and metamorphic testing together with bounded exhaustive input generation and input minimization. We apply TestMC in testing for different model counters from 3 different classes. Specifically, we test projM, and dSharp, which are exact model counters, Ganak, which is a probabilistic exact model counter, and projM, which is a probabilistic approximate model counter. We use 3 different test suites as input formulas for testing. TestMC was able to find bugs in 3 of the 4 subject model counters. These bugs included crashes, segmentation faults, incorrect model counts, and resource exhaustion. 2 of the tools were corrected after our bug reports, whereas the authors of the 3rd tool thought that the tool doesn't require a fix. We'll explain why is that the case. So model counting is basically the problem for finding the number of solutions to a formula over a bounded universe. It has many recent applications in planning, knowledge compilation, program analysis, reliability, and security. These model counters are really complex in the algorithms they employ, so it is really important to check their functional correctness. That's why TestMC is one of the framework for testing their correctness. It uses 4 well-studied approaches from software testing. For example, it uses bounded exhaustive input generation, which is where a system under test is tested against all non-equivalent inputs. Differential testing, where outputs of multiple systems is compared, and the one which is different from all others is considered to be likely faulty. Metamorphic testing, where metamorphic relations among results for different inputs are used as surrogates for test oracles. Input minimization is where the inputs that cause failures are minimized so that they can be create like smaller examples which can still reveal the faults are created. So these all principles are used in TestMC. In terms of our contributions, the first contribution is the framework itself. As I said, it uses 4 well-studied approaches from software testing. We define 1 sanity check and 4 metamorphic relations as test oracles. These utilize domain knowledge, so these can also be used for other SAT solvers as well as SAT solving problems. We conducted a study where we tested 4 model counters using a set of 3 different test suites, and we also present a set of lessons learned during our experience of testing model counters using TestMC. So coming on to the model counting, we can consider the Boolean formula F, where A and B are Boolean variables. We can see that there are basically 4 possible assignments to this formula, since there are two variables there, but only 2 of them are the possible solutions. So model counters and most of the SAT solvers kind of take the input in a DIMACS CNF format. So we can see on the right-hand side of the slide, there's a figure there where PCNF basically specifies the type of the formula, which is CNF. The first 2 on the first line says the number of total variables in the formula, and the last 2 says what is the total number of clauses. So there are 2 variables and 2 clauses. Each variable is basically represented using an integer ID. For example, A is represented by 1 and B is represented by 2. The negation of a variable is represented by the negative of that integer ID. So for example, if we want to represent A or not B, we use 1 minus 2 to kind of represent this form of this clause. Whereas all DIMACS format requires to insert a 0 at the end of each line so that the solvers know that the clause is ending there. So that's like the DIMACS format which the model counters and the subject study also take as input. Coming on to the projected model counting. So what is projected model counting? Let us suppose the formula G here, A and B or C and D. This is not in CNF, so we really want to convert it into CNF using logical equivalences. But that can that can bring an exponential increase in the formula size. So what the recent model counters are doing, they introduce auxiliary variables, for example, U and V, and translate the formula G to H. It might look at it's a different formula, but the satisfiability is the same, although the model counts differs because now the state space is not 2 power 4 equals to 16. That's not the case anymore. It's 2 power 6 equals to 64 now. So projected model counters basically project the model counts on the original variables A, B, C, and D, which we call the primary variables, and that's how the count also remains the same, and we also don't get an exponential increase in the formula size. So that's how projected model counting works. So this slide basically shows some of the example failures in Ganak, dSharp, and projM. So if you look at the formula A, it is basically a contradictory formula. So it is like A and not A. So we know that cannot be satisfied because the number of solutions for this formula are always 0. Whereas when we use dSharp, it output a model count of 1, which is obviously wrong. So there seems to be a bug in dSharp. For Ganak, it gave like an assertion error in this formula. And there was another long formula, which due to space limitations, I cannot show here. They are available at our GitHub repo. On that, projM gave a segmentation fault. So we see that these three model counters do have some kind of bugs in there. Coming on to the boundary exhaustive generator, we have a boundary exhaustive generator which can generate CNF formulas. Max variables and max clauses are basically the bound on the input side. So max variables is the total number of variables, the maximum number of variables in a formula, and maximum clauses is the maximum number of clauses in the formula. So what the algorithm actually does to simplify is that it basically, if there are 4 variables, it creates 8 literals out of them because there is like negation of each variable as well. And out of those 8 literals, it creates all possible set of clauses which are 2 power n, and then it kind of filters the clauses which are like which are tautological clauses because their assignment doesn't affect any model count, and we also remove the empty set. So we get like a filtered set of clauses, and from those set of clauses we create all possible formulas. If there are 2 formulas where the clauses are the same, it's just the order which is different, we also filter out those formulas, and that filtering is required because in bounded exhaustive generation, the input, like there can be an exponential increase in the number of CNF formulas generated. So symmetry breaking is really required there. So for example, we use 4 variables and 4 maximum number of clauses for the formula generation, and still we got like over 6 million CNF formulas. So symmetry breaking is really required there. Coming to the differential testing module, so what we do is like we run each model counter on each of the input formulas, and then we compare their outputs with each other. So if there are like 4, we have like 4 subject model counters. If there is one of them which predict a model, which gives a model count which is quite different from the other 3, we consider that as a likely fault. So one question which comes up right now is that we have a probabilistic exact and probabilistic approximate counter, right? So there can be like differences in their output. They are not exact model counters. So for this, we based on a study done recently in 2020, we set a tolerance value for projM and Ganak, where if the study says like if it's within 10%, that's appropriate. So if these 2 model counters gives a count which is more than 10% different than the other 2 model counters, only then we consider them to be a faulty. This is a user-based value, so the users can provide that value. Coming to the metamorphic testing, we consider F to be a formula in positional logic with n variables. The possible number of assignments is 2 power n. K are the primary variables. P and C is basically the projected model count for F. So the first sanity check we have is that the projected model count should always be less than equal to 2 power k, because 2 power k is the maximum number of possible assignments, so the model count can never exceed that. In terms of the metamorphic relations, what we do is like we have the original formula F, and we create a variation of that formula F, which we call F prime. And then based on the variation we created, we see what kind of a relation should exist between the model counts of formula F and formula F prime. So for example, in MR1, what we do is like we take a variable from formula F and we fix its value to true. And that means like the total number of model counts should be less than equal to the original formula, because like all the possible solutions where the value of variable V was false gets removed, right? So the number of new solutions should be less than the original one. It can be the case that all the original solutions already enforce the same rule that where v variable was held true. In that case, the count should remain the same. So that's why we have this sign greater than equal to, like the original formula should be have a count greater than equal to the new formula. MR2 basically follows from the same MR1 relations, where in one for f prime we fix the value of v to true, and in another we fix it to false, and then the sum of them should equal to the original formula count. In MR3, what we do is like we add repeated literals to randomly pick clauses. So if we have A or B, we make it A or B or A. So that shouldn't affect the model count as well. In MR4, we add tautological clauses. So our tautology is always satisfied. So that shouldn't affect the model count as well. So the model count for F and F prime should be the same. So these are some metamorphic relations. The mathematical details are in the paper. So these, coming on to the test suites, we basically use 3 test suites. The table summarizes the basic details about them, like the min, max, and average number of variables, primary variables, etc. So SDP Gen is a 203 is a suite of 203 large CNF formulas that are from software design problems. So there is an Alloy tool set which basically comes with these 203 large CNF formulas. And Alloy is a tool which can model real-world problems with CNF formulas, and it is a really famous tool. And the CNF it provides is a valuable source for testing model counters. The second test suite is BEGen, which is basically consisting of 6.65 million CNF formulas generated by our TestMC boundary exhaustive generator, which we described earlier. FirstGen is the third test suite. It consists of 10 million formulas, and it is these formulas are generated using off-the-shelf sets CNF fuzzer called FFuzzer. So we have like around 17 million formulas in total to test. So TestMC is able to find 4 different type of bugs. WSAT bug, which is when a model counter returns a satisfiable solution for an unsatisfiable problem. WCount is when the projected model count is wrong. Seg fault is when the model counter experiences a segmentation fault, whereas a crash bug is when it terminates unexpectedly. So we evaluate our test tool using 3 different research questions. The first one is about the effectiveness of differential testing module. So we found that TestMC found 2 types of bugs: WCount in around like 4 million CNF formulas, and crash bug in around 57,000 cases in Ganak. So that definitely points out that there's some problem with Ganak too. For dSharp, TestMC found 2 types of bugs: WSAT in around 56,000 cases, and on 18 formulas, dSharp simply crashed. For projM, there were like 2 formulas on which it gave segmentation fault, and there were no formulas on which ApproxMC gave a wrong count or crash. So we can see that differential testing really points out that they're it's really helpful in finding and categorizing bugs in model counters. Coming to the metamorphic testing effectiveness, what we do is like we pick the formulas which in RQ1 gave different counts, like for the formulas on which Ganak or dSharp gave a different count than other model counters, and we use those formulas as input, and then apply our 4 metamorphic relations and the sanity check. We are only applying these on those formulas because TestM's, like the metamorphic relations, require 1 additional invocation of model counter for each formula, which is quite expensive. So we only use it to confirm that the problems found during differential testing are the correct ones. For Ganak, SC1, MR1, and MR2 proved to be really successful, figuring out like around 73.5 and around like 50% of formulas. MR3 and MR4 were not able to find any bugs, but their importance shouldn't be underlooked because these problems did not exist in these model counters. So I mean, we should still keep them and use them for other model counters. For dSharp, MR2 identified around 25% of formulas on which TestMC during differential testing identified WSAT bug. And there were like total of 15 formulas on which 1 or more model counters timed out, and 20% of these formulas violated metamorphic relations. So we could confirm more and more bugs in the model counters. So we can see that overall the metamorphic relations also serve useful in finding bugs for model counters. Coming on the input minimization with delta debugging, what we do here is like we take an input formula on which Ganak or a particular model counter crashes. We generate 2 formulas, C and D. So C is basically a subset of all of the original formula, and D is also similar to C, except that D contains 1 more additional clause on which the model counter crashes, but it doesn't crash on C. So we can see, like, compare the trace output, execution trace of the model counters on C and D, and then try to figure out how is it different because of just one clause, and why does it crashes? And it really helped us to figure out pinpoint the exact location of crash bug in the Ganak tool. And on every TestMC was able to remove 30% of those clauses. Number of unique bugs, W count bug and crash bug were found in Ganak. All crash bugs in Ganak were assertion errors at the same point in the code. W count bug were related to incorrect parsing of projected model count variables. So we consider them as two separate bugs. For TestMC, crash bug was because it was using maximum memory available on the operating system. So the operating system kind of crashed. So, and WSAT is like we talked with the authors and they confirmed that the tool can only work on satisfiable formulas, not on unsatisfiable formulas. So these are like two different things. So we considered them as two unique bugs. For projM, there was segmentation fault, but it's a proprietary code. So we were not able to get the source code. So we were not able to exactly study the reasons behind the segmentation fault. But the authors kind of corrected the tool and sent us a copy of the correct one. So in terms of more comprehensive testing, we can adjust the model counters configurations. We can also increase the timeout from 5,000 seconds to a much higher value. 5,000 seconds is the most commonly used in model counting, and there were only 15 formulas on which model counting like timed out of those 17 million formulas. So it really doesn't bring much of a problem. We can turn the symmetry breaking off, so we can get more and more formulas here. Coming on to the lessons learned, we see that the definition of fault can be surprisingly ambiguous. For dSharp, we consider that if it gets a model count of 1 instead of 0, it's a fault, but the other said it's lack of functionality. Small input formulas were extremely useful in fault localization, as we figured out that we were able to figure out the bugs, reasons of the bugs in Ganak using small input formulas. And the problem in Ganak was in assertion error. So Ganak is a complex tool, so we can see that developers usually overlook simple things like dealing with assertion errors while they're concentrating on the main algorithm. It is difficult to help debug proprietary closed source software because we don't have the source code for that. Some model counters can consume all system memory, so we should run them in particular maximum memory containers so that they don't crash our operating systems. And some of the public versions of the tool may remain faulty even after the bugs have been fixed. So for example, for projM, even after 6 months, the public version wasn't corrected. So coming on to the related work, to our knowledge, our paper is the first study of testing propositional model counters using differential and metamorphic testing. There has been some work in terms of testing set solvers and testing of SMT solvers. So for example, one researcher introduced novel fuzzing techniques for SAT and QBS solvers. He also proposed grammar-based black box fuzz testing for randomly generating.
Mohammed, you're going to have to finish in the next soon.
Yeah, I'm just finishing it up. So there is like some work in SMT solvers and constraint propagation solvers. So coming to the conclusion, TestMC is a framework for testing industrial strand model counters. We use principles from differential and metamorphic testing. We tested 4 model counters from 3 different categories using 3 different test suites of input formulas. The bugs led to crashes, segmentation faults, incorrect model counts, and resource exhaustion by the solvers. Faults in 2 of those 3 model counters were fixed by their authors based on the bugs report found by TestMC. So that's all with my presentation, and I'm excited to hear questions from all of you, and thank you for listening to the presentation.
Can everyone unmute for 5 seconds and just join with me with a round of applause for our author? Thank you very much.
Thank you.
That was pretty bad of you for unmuting. Thank you. More unmuting. Thank you. Thank you. Okay. Any questions for our speaker? Nothing in the session Q&A. Mohammed, have you got any examples where you've taken your stuff and gone back to prior publications and just wanted to tell us that certain prior publications got really a lot of things very, very wrong?
Yeah, I agree that there are some conferences where we cannot like directly take results from them because there needs to be more validated as well. But what we did for that tolerance value was like the first thing is that the user can supply that tolerance value, that 10% thing. So if we decrease that value, there are chances for more false positives. And we also did determine, we ran some certain sets of experiments to make sure that the paper we are referring to, the value they give. So the value they give actually is like the probabilistic model counters kind of vary in around like 7-8% margin. And in our experiments, what we found was like it varies from 5 to 10%. So just to be on the safe side, not to get false positive, we kept the value to 10%. But the user can specify this value according to his or her demands.
Okay.
This is like a user's client value.
Thank you very much. Very good. So